Okay, thank you, Brian. And thank you, Milrak and Brian specifically um, for this opportunity. Good morning, good afternoon, everyone. My name is Jayasree Srinivasan. Please call me Jay. I'm a research scientist at Baxter BioPharma Solutions in Bloomington, Indiana. So I've been with Baxter for almost 8 years now, primarily focusing on formulation and lyophilization process development. And we conduct a lot of research studies. We are primarily a CMDO, but we also conduct research studies to enable publications in the betterment of the field in general. So one such study that I recently conducted was on the graphical design space for primary drawing. Most of you know that we develop what's called a graphical design space to optimize the primary drying conditions during lyophilization. So what are the sources of variability associated with the dry product layer and the product resistance within the design space? And how does that impact the cycle design is the focus of my presentation today. So just to give you an outline of what this discussion is going to be. So we will talk briefly about QPD, which is quality by design, why that is important and why it's relevant to our industry. And then we will go on to talk about the elements of a graphical design space. And then we will focus on the product resistance, which is RP. So this investigation started with an assumption that the RP is primarily constant within the design space of a given formulation. So what did we find out looking into that specific aspect of product resistance? And then we look at the formulations that we used for this study. We will analyze the data a little bit, and with the conclusions, hopefully we'll have a couple of takeaways from the study and possible studies to answer some more questions. So what is quality by design, right? It is a multidimensional space, and more the pharmaceutical industry is adapting to this quality by design, wherein you develop this based on sound scientific knowledge rather than empirical or based on trial and error experiments. So these could be, so as I said, these are scientifically designed based on a few performance criteria, and it could be based on prior knowledge that are already existing in the literature. And then you would develop experiments that are not redundant, but based purely on a thorough understanding of a given formulation. So this is just a representative design space here. So what it is a multidimensional space where you have more than two variables associated with this design space. Here you have, this is primarily for the primary drying optimization with respect to lyophilization. This would be a graph of the sublimation rate on the y-axis versus the chamber pressure on the x-axis. So it encompasses a series of process conditions within this yellow region, which is called the safe zone. But then there are two boundaries that are associated with this design space. One is this red line, that is your equipment capability line. So that would be unique to the equipment that you are working with. And the other line here, the black line, is your collapse temperature, so which will be specific to your formulation. So this design space method is purely based on what the collapse temperature is for your given product, what the equipment quality capability is for your lyophilizer, and also some of the parameters that are involved in developing it. So if you look at the design space, with respect to how we generate it using an Excel-based Lyo calculator that Professor Pical and Steve Nail established several decades ago. So like I said, it's a graph of sublimation rates versus chamber pressures. And this green space here is your design space. So how do we construct this design space, right? So you know your product temperature, the collapse temperature of your product, which is the solid red line. And you also know the capability limits of your equipment, of your dryer, which is this blue line. So within that, using that, the macro of the Excel spreadsheet, the Lyo calculator, you would input certain parameters, such as the KB, the vial heat transfer coefficient, the RP, which is your product resistance, that is unique to your product, to your formulation. And also you would put in the other input parameters would be your shelf temperatures and other product temperatures. So these are basically you're leveraging that calculator to calculate the sublimation rates at various shelf temperatures and product temperatures. So using that, you would come up with this green zone that is well inside your capability limit and the product temperature limit. So the assumption is that as long as you stay inside this green space using any combinations of shelf temperature or chamber pressure, you should be able to obtain an acceptable product. And the assumption is that the RP, the product resistance, will be stable, constant within this green space, the safe zone, right? So that is where this investigation started. So an intern, Ray Fang, some of you may have been familiar with her or worked with her in the past. When she interned at Baxter more than 7-8 years ago, she did a limited study due to time constraints on a formulation containing 5% mannitol and 5% sucrose. And then she evaluated a couple of shelf temperatures, minus 25 C and minus 15 C for that particular formulation, at a couple of chamber pressures. And what she observed was somewhat similar product resistance for each of the process conditions. But then again, like I said, that was very limited data. So we wanted to probe that further. So that was the goal of this study for a better understanding of RP. And then what are the factors that are affecting RP? Does the RP stay the same within the green space, or does it vary? And how does it vary depending on the process conditions? So we chose 3 formulations, one that was representative of an amorphous system, another one for a crystalline system, and the third system was a mixed system containing both an amorphous excipient as well as a crystalline excipient. And then cycles were conducted to obtain RP data, to generate the RP values for these 3 formulations. And from there on, we built a design space for each formulation. And then within the design space, we conducted a series of cycles using various combinations of shelf temperatures and chamber pressures. And we used the TDLAS, which is the tunable diode laser absorption spectroscopy, to collect the mass flow rate. So in terms of the 3 formulations, formulation 1, like I said, was amorphous in nature, and we used BSA as the model protein at a concentration of 10 mg per ml. So for formulation 1, we used sucrose at 3% weight to volume. It did not contain mannitol because we wanted to keep it completely amorphous. And it did contain histidine as the buffer at a pH of 6.0. Formulation 2 was the crystalline system. So that did not contain any sucrose, whereas it contained mannitol at 3% weight to volume. And the mixed system, formulation 3, contained both sucrose and mannitol. And the fill volume was 5 ml in a standard 10 ml short vial, except when we use top Lyo vial, which I will specify later. In most cases, we use the standard short vial. So the first step that you would conduct as part of the development group here at BPS, we would conduct low temperature thermal analysis just to get an idea as to what the failure point is, what the collapse temperature is for the particular formulation. So for that, we leverage DSC and freeze-time microscopy. So using these two studies, we found out that for formulation 1, which is your sucrose formulations, I have a little table here, just so I don't have to repeat it. For formulation 1, the collapse temperature was about where you would expect for a sucrose formulation, which was minus 32.5 degrees C. And for formulation 2, the crystallization temperature, because it contained mannitol in it, was minus 22.7 degrees C. And failure temperature, the eutectic melt, was observed at minus 8 C. And then formulation 3 being a mixed system, we observed a collapse at minus 18 C, and the crystallization temperature was a little warmer than it was for the mannitol formulation. So these are some images during collapse or failure of the 3 formulations. So in terms, and then the next step was to go on to doing a full lyo cycle for the 3 formulations with an intention to generate the RP values and construct a design space for each of the 3 formulations. So the lyo cycles pretty much looked similar for the freezing step, which was down to minus 40 C, and we would hold it for a couple of hours. And the secondary drying step was also identical, with that performing at 40 degrees C at a chamber pressure of 100 milliliter for 10 hours. So what varied was the primary drying conditions, the parameters. For formulation 1, the primary drying temperature was minus shelf temperature was minus 25 C. And then for formulation 2, in addition to the freezing step, we also had an annealing step just to encourage mannitol to crystallize completely, which was performed at minus 15 C. But primary drying was conducted as at minus 10 C. And for the mixed system, primary drying was performed at minus 20 C. So with that, so just to give you a little bit background on the TDLIS, if you have not used it already. So what it does is it optically measures the water vapor concentration. So it is usually located in the duct area between your the dryer chamber and the condenser. And then the TDLIS, it has 2 lasers that are positioned vertically, intersecting each other. And it measures the water vapor concentration and the gas velocity in the duct region, in the spool piece region. And using that information, it determines the water vapor concentration, the removal rate, which is your sublimation rate. And then it also interpolates it to determine the total amount of water lost during sublimation and also during secondary drying. So I'm not going to go over the mathematics behind how the TDLS works. And then for the RP calculation, as you can envision, RP is influenced by the components present in your formulation, because it's different based on if your formulation is amorphous or crystalline. It also depends on the fill volume, as you can imagine. And then the product area of the vial. So if you can visualize having a 5 ml fill in a wider vial versus a narrower vial, you can imagine the RP is going to be much higher for the narrower vial than for the wider vial. So these are the factors that influence the RP, and this is the principle, the mathematical principle that governs RP, which is that RP is inversely proportional to the mass flow rate, as you can imagine, and it directly is proportional to the area of the product inside the vial, which is the vial inner area, the diameter, and also the difference in the vapor pressure of ice at the sublimation front, which is PI, and also the chamber pressure, which is PC. So this is just a comparison of the mass flow rate that we obtained using the TDLAS, which is the red line here, and the blue line, which is the RP data that we calculate using your product temperature and also the equation that I showed previously. So you can imagine how, you can see how well the two data correlate and compare. So if you look at the RP line, so RP increases, this is just a representative curve for this particular formulation. RP increases slowly, and at about 20 hours or so, it rises steeply. So that presumably is the end of primary drying. And then if you look at the mass flow rate, it's steadily decreasing, but around the region where the RP increases steeply, that is when the mass flow rate also decreases sharply. So that shows you that the TDLAS data that we typically use for our calculations is reliable and correlates well with the thermocouple data that you typically use to generate the RP data. Just to summarize the product performance, all three formulations with respect to the sublimation rates and the product temperatures and the RP. So you can see that for formulation 1, the process conditions are here. I'm not going to repeat it. The sublimation rate was at about 0.08 during the steady state sublimation step. And then the product temperature was also minus 32.5, again, during the steady state sublimation. And the RP was calculated to be about 8 RP unit. And for formulation 2, just to remind you, which is the crystalline formulation, the sublimation rate was much higher, almost a twofold increase in the sublimation rate for this formulation. And the product temperature, as you would expect, was much higher because it contained mannitol in it. It was minus 24C. But then when we calculated the RP was much higher for the mannitol formulation than for the amorphous formulation. So how did formulation 3, the mixed system, behave? The sublimation rate was somewhat similar to the amorphous formulation 1, with the product temperature in between the two systems, the amorphous and the crystalline systems. And the RP was closer to the sucrose formulation. So what is the next step then? So with that data, the RP data, you know your vial KV and you know your collapse temperatures, the next step would be to construct the primary drying design space for the 3 formulations. So again, the governing principle is given here. So what we know, so these are the input parameters before you start your lyo run or your AV, that's the vial area, the shelf temperature that you're going to utilize for primary drying, then the cake area, which is the vial inner diameter and the vial inner area, the heat of sublimation, which is a constant, and the chamber pressure that you're going to utilize for your cycle, right? So these are all known parameters. So what you would measure using the TDLAS would be your dm over dt, which is the mass flux. And what you would also measure would be your product temperature, because you would be using product thermocouples. So what you would calculate using these equations, using the first principles of heat and mass transfer, would be your dq over dt here. That's your heat flux, and also the vapor pressure of ice at the sublimation front, which is the pi. So kV presumably was already obtained from a previous cycle, and also RP from a different cycle. So this was the design space we obtained for the sucrose formulation 1, wherein the yellow circle here, the orange circle, I should say, was where the cycle was conducted using a shelf temperature of minus 25C and a 100 millitorr chamber pressure. But then what the design space tells us is that you can run that particular cycle more aggressively than we did here, in the sense that I could have run my cycle at minus 15C and a chamber pressure of minus 40 or 50 millitorr. So this is how the design space is going to help you during your process development. So imagine running your cycle at minus 15 C shelf temperature versus minus 25 C. So you're going to tremendously improve your cycle duration. You're going to cut down on the cycle time, the primary drying time, if you were to run your cycle here versus here. So with that knowledge, the next step was to actually evaluate various combinations of shelf temperatures and chamber pressures within this green zone and see how the RP values compare for each cycle. So we chose a series of conditions here represented by different colored circles. And then one circle above the design space, about the green zone. I'll tell you why I evaluated that particular condition later. And then we conducted a series of cycles, about 7 of them, and then evaluated the process parameters and also calculated the RPs and compared them. So if you were to neglect this first cycle, which was outside of the design space, if you compare the RP data, so you started, the lowest was about 7 and the highest was about 13. So you see a twofold increase in RP based on the process conditions. So the most aggressive cycle was minus 20 C 15 millitorr, for which the RP was the lowest. And then the most conservative cycle was at minus 35 C and 50 millitorr, wherein the RP was about 13. So this was the general observation for all three formulations, in the sense that there was an inverse relationship between the RP and the sublimation rate. So I forgot to mention the sublimation rate. Sublimation rate was highest for the most aggressive cycle, which you would expect, and also the lowest for the most conservative cycle. So there is an inverse correlation between RP and the sublimation rate. And also the other thing that I wanted to point out is that, for example, for this particular cycle, where the calculated product temperature was, the product temperature observed using the thermocouple was minus 33.3. Whereas if you look at the calculated product temperature over here, this particular cycle, it should have been about minus 31 or so. Right. The reason why we see this discrepancy probably was because of the placement of thermocouples. There are a lot of uncertainties associated with thermocouples with respect to the placement, how the when sublimation progresses, how the ice is concentrated at the center of the vial, and that kind of makes the thermocouple move around a little bit, and also because the design space was calculated using a constant RP. I told you we ran one cycle to generate the RP data. So it was based on that particular RP, a constant RP, whereas here it was calculated, but the actual product temperature was due to varying RP, because as the cycle progresses, the RP changes, right? So that is why you see some differences in the actual and the calculated product temperatures. So moving on to formulation 2, so we did a similar exercise to generate the design space, and this is what we obtained. Yet again, the cycle we conducted was down here, the yellow, the orange circle, whereas the most efficient cycle would have been somewhere here at a shelf temperature of 20 C and a chamber pressure of 110 millitorr. So we did the same thing here, wherein we looked at a series of process parameters within this design space. And then conducted that many cycles and then generated that many RP data and the sublimation data. Again, the same trend of an inverse relationship between the RP and the sublimation rate still held good with this particular formulation. In addition, if you look at the RP values by themselves for this particular formulation, the highest RP we observed was 12.2, but the lowest was 9.2. For the sucrose formulation, if you remember, the range was between 4 and 13, or 7 and 13, depending on if you take that cycle that was outside of the design space into consideration or not. But for this particular formulation, the RP was much tighter than it was for the sucrose formulation. And the sublimation rates were a lot higher, as you would imagine, because the shelf temperatures were a little higher as well. So regarding slide number, there is a question that came through slide number 16, why the values of pressure and shelf doesn't match with the correspondent mass flow. Again, there are differences, same differences like I told you previously with respect to how the RP was, how the design space was calculated using a constant RP, and then how these different cycles pan out with respect to varying RPs within the same cycle. So that is the one that gives rise to different sublimation rates, the observed versus the calculated. I hope that answered the question. And then we already went over this data. And then the reason why I conducted that particular cycle for the sucrose formulation, which was outside of the green zone at -10C and 100 milliliter, was to compare the data observed for that formulation using those conditions with the mannitol formulation, because mannitol, since it's crystalline, you have the ability to be able to conduct your shelf cycles at more aggressive conditions than for sucrose. And I only had a couple of data points that were like direct comparison of the two formulations. So one of them was -10C at 100 milliliter. For formulation 1, which was your sucrose formulation, the product temperature was much lower than for the crystalline formulation. But then if you compare the RPs, you can see a drastic difference. For the sucrose formulation, it was 4.0, which was much lower than 11.8 that we observed for the mannitol formulation. So RP is dependent on the formulation. And we already showed in the previous slides that RP varies depending on what process parameters you use within the design space of a given formulation. So just to compare the process data with respect to the two formulations for another cycle conditions, which was -20C and 50 milliliter, again, you see a big difference in the RP data for the two cycles, right? And just to pictorially show you how the differences manifest with respect to the two formulations, the gray line here is the RP graph, RP line for the sucrose formulation. As you can see, it is pretty constant throughout. As soon as sublimation starts, when the shelf temperature reaches the temperature set point, from there on until the end of primary drying, it is relatively constant. The RP is constant. And then it increases sharply at the end of primary drying. Whereas if you look at the same RP graph for formulation 2 for the mannitol formulation, the RP increases steadily until the end of primary drying, and then it increases sharply. So there is a big difference in the behavior of the two formulations with respect to the product resistance. And then you see a similar difference in the mass flow rate data as well. For the sucrose formulation, since the RP is constant, the mass flow rate is also relatively constant until at the end of primary drying, when it declines sharply. Whereas for the mannitol formulation, there is a steady decrease in the mass flow rate, right, until the end of primary drying. So what is the reason behind the mannitol formulation or the crystalline formulation exhibiting a higher RP than the amorphous formulation? Our hypothesis is that in the crystalline formulation, mannitol obviously crystallizes. We also had an annealing step just to ensure that all the mannitol crystallizes. So the crystallization of mannitol somehow disrupts the freezing behavior and the ice porous and the ice crystallization as well. So and the ice porous structure. So that results in the water vapor during sublimation. The water vapor it encounters a tortuous path for sublimation in the crystalline formulation, whereas in the amorphous formulation, it's only the ice that crystallizes, and everything, all other components remain amorphous. Probably the ice path, the water vapor path is more straightforward than it is for a crystalline formulation, is what we think is happening. Okay, so now we know we have some data with respect to the amorphous and the crystalline formulation and the actual behavior of the two formulations with respect to the product resistance. So what is it that we can change within the formulation? Not changing the formulation, keep the formulations the same, but then change the process parameters or change the nature of your components so that you're able to flip the amorphous formulation into crystalline or crystalline into amorphous nature. With sucrose, you cannot make it crystallize, whereas with mannitol, you can make it not crystallize during the freezing step. So that's what we exactly did. So we attempted to maintain retain mannitol amorphous by either flash freezing in liquid nitrogen or conducting the freezing step as fast as the dryer is capable of doing. So for our Lyostar 3 dryer, that freezing rate is about 2 degrees C per minute. So for this particular cycle, which had used the fast freezing step instead of the flash freezing with liquid nitrogen. So this is what we had obtained. So I did X-ray powder diffractogram to see if mannitol remained amorphous or not. For most part, it remained amorphous. We also saw a little bit of mannitol crystallizing because presumably 2C a minute is not fast enough to prevent mannitol crystallization. So regardless, so we went ahead and conducted primary drying and secondary drying with this amorphous mannitol formulation. And here we are comparing the two data of the mannitol formulation, but one crystalline and one amorphous, the other amorphous. Same shelf temperature and chamber pressure. The sublimation rates are different here in this case. For the crystalline formulation, the sublimation rate is low. It kind of is 0.09 for this particular parameters that we used. And for the amorphous formulation, it was much higher. And the product temperatures flipped in the sense that for the crystalline formulation, it was much higher, whereas for the amorphous formulation, it was lower. And then if you look at the RP, that we were surprised with this result. For the crystalline formulation, for the crystalline mannitol, it was 12.2, whereas for the amorphous mannitol, it was 4.5. So this, so the amorphous mannitol behaves similar to the sucrose formulation. So that tells you that this lower RP is probably unique to the amorphous nature of the formulation, and the crystallinity of your excipient affects the RP directly, and it increases it during sublimation. So moving on to the mixed system, which contained both sucrose and mannitol, we did a similar series of cycles within the design space. But then if you look at the RPs are even tighter for this particular formulation than it was for the crystalline formulation. It ranged between 7 and 9, which are definitely lower than we had observed for the mannitol, the crystalline mannitol formulation. So this, the mixed system presumably behaves similar to sucrose, so more closer to sucrose than to mannitol is the bottom line here. So if we were to compare, again, the RPs of the three formulations and also side-by-side comparison here, and also the amorphous mannitol, here you can see clearly for the sucrose formulation, like I said previously, the RP remains the same during sublimation, and for the amorphous mannitol formulation, it remained about the same. Since there was a little bit of mannitol that had crystallized, that probably impacted the RP in the sense that it increased slightly during sublimation, but not as big a deal as crystalline mannitol. This kind of a constant RP for amorphous formulations is not new. It has been observed previously and has been reported in the literature. So you can look at these two articles. So that suggests that the sucrose behavior is somewhat expected, but the crystalline formulation behavior is, and the amorphous mannitol formulation behavior were somewhat surprising to us. Here I've just shown you. The other experiment that we performed was the top lyo. So again, so we want to maintain mannitol crystalline. So we already answered if your crystalline component remains amorphous, it behaves similar to an amorphous formulation in lowering the RP. So how about okay, so what if in amorphous formulations, with sucrose formulations especially, you observe shrinkage? It's very common. So what if the shrinkage is the one that's responsible for lowering the RP? Obviously, the shrinkage, by shrinking, what you basically do is to open up pathways along the sides of the vial, right? So that probably increases additional pathways, provides additional pathways for the water vapor to escape during sublimation. Maybe that's why the RP is lower, right? So in order to probe that hypothesis, what we did was we used the mannitol formulation, crystallized it during the freezing step, but used a top lyo vial instead of your standard short vial. So top lyo vial, as you know, it has this hydrophobic coating that results in the cake, the freeze-dried solid separating from the wall vial, right? So because of the shrinkage. So we wanted to see if that had an impact. So we did this cycle using a top lyo vial, and this is what we observed. So the orange capped vials on the left are the top lyo vials, and the two vials on the right are the standard vials. We did observe shrinkage with respect to the formulation, the mannitol formulation, but what we did not observe was a lowering of the RP. The RP remained about the same. So this implies that it is not the shrinkage that decreases the RP. It is rather the crystallization of mannitol in the crystalline formulation that increases the RP due to the tortuosity associated with the crystallization of the excipient itself, and for the water vapor escape during sublimation. So we went ahead and characterized the freeze-dried solids for surface areas. Using this instrument, the micromeritics ASAP instrument. So it has a dual chamber that enables us to characterize two samples at once. And we use the vial assays. We do not do any sample preparation. So this is just a summary of all the data that we obtained for this particular analysis, specific surface area analysis. The bottom line is that the RP, so if you compare the BED surface area versus RP, for the sucrose formulation, the lower the RP, the lower the RP, the surface area. So there is a direct correlation between the RP and the surface area. And for the crystalline formulation, formulation 2, the surface areas are higher than those are for the amorphous formulation. That's also very apparent. So there is an inverse relationship between the sublimation rates and the surface areas. And then for the amorphous formulation, The surface area was similar to that of the sucrose formulation because the RP resemble the amorphous formulation RP. So in terms of implications of this study, so we observed that RP is not constant for the same formulation. The RP is not constant within the design space. It varies based on the process parameters you use. And the higher the sublimation rates, that is the higher the shelf temperatures that you use for your cycle, the lower the RP. So we have a couple of hypotheses for these observations. The reason why for more aggressive cycles, the RP is lower is because probably it has to do with the microstructure. With aggressive cycles, you are probably cause the higher sublimation rates are causing more of an open structure, and that lowers the RP. So that is, and this is consistent with the surface area result as well. And then the reason why you see a difference in the RP with the RPs within the same formulation could be because the flow behavior during sublimation of the water vapor changes. We are probably changing between molecular flow to a viscous flow that results in different changing the RPs. So these are our hypotheses. We need to probe these further. But for now, these are our observations. So it would be prudent for you to choose cycle parameters that are, closer to the apex of the collapse temperature and the equipment capability limit curve, but then staying within or below, under the apex, because you do have edge vials that are much warmer than the center vials. But then choosing conditions that are that provide the maximum sublimation rate is going to be your most efficient cycle because it's going to be your fastest cycle. So in terms of conclusions, so what we set out to do, we were able to achieve that because we wanted to probe if RP remained the same throughout the design space, and it turned out to be not true. And then RP was dependent on the cycle parameters, obviously. But then for aggressive cycles, RP tended to be lower than for more conservative cycles. And then RP was much lower for the amorphous formulation than it was for the crystalline formulation. And then I went over all these already. So in the interest of time, I'm not going to go over every single point. So we are right at about time, but there were a few questions that already came through, and I wanted to take this time to address that. But then before I do that, I wanted to acknowledge Greg, Sasha, and Steve Nail. They were involved in this project. And then the Baxter BioPharma Solutions, the R&D group. And just so you know, if you are interested in a position in our group, we are hiring. Please feel free to reach out to me. My email is in the bottom. And Milrock for this opportunity. They have a much wider audience, and I'm glad that they reached out to me for this webinar. And thank you all for your attention. So I'm going to go back to the questions that are already posted, and then Brian, maybe you can help me with any new questions that I'm not able to see here.